Hi, this is Dave Redder, and I'm teaching a course in the Introduction to Languages and the Theory of Computation using the book whose cover you see right there. And I'm going to make a couple of lectures here about Turing machines available to my students via YouTube. So the book does a nice job of describing where Turing machines came from and what we mean by a model of computation and what we mean by a general model of computation. And I'm going to go over some of this material with you. As we know, we've already discussed things about finite automata and push-down automata and the equivalent generation or accepting facilities that you get through regular expressions and context-free grammars and various things like that. And we know some things from our previous study that would be hard to come by on your own, but these guys did it. They're pretty amazing people, and they did it back in the 1930s, a lot of it. An example of something that I'm talking about here is that this simple PAL, which PAL stands for palindrome, it's the set of all strings that start out with a string followed by the letter C, followed by the original string but in reverse order. And that's a simple palindrome. A palindrome is a word that reads forwards and backwards the same, like Ada, for example. In this case, ACA. It can't accept this. And a device with only one stack can't accept that. But then they point out that if you had two stacks, then you could accept AN, BN, CN. And one of the members of the course asked, does that mean that it can't accept AN, BN, CN, DN though? And that's not the case, but it's a great question, I thought. The reason is because now with two stacks we can take things off of the one stack, push them on the other, so we don't lose track of our count, which we do trying to use it with one stack. We've discussed all that in the past, and if you're not part of this class, you probably won't understand what I'm talking about in part of these things because it's examples we've used in the past. Well, Alan Turing is a brilliant human being, or was a brilliant human being, who helped this world in 100 different ways, but among them was that he considered the concept of what a general model of computation might be. And he did this in part by imagining a human sitting there with a pencil and paper trying to figure out something, some problem. And what can this human do? And he came up with these three rules that you see right here. And the three rules are that you can examine an individual symbol on the paper, and we're thinking about processing a string of characters in some sense, all right? Like we've done with FAs and like we've done with PDAs. And then he says we can erase the symbol and replace it by another, or not erase it if we don't want to, we'll just leave it alone. And then we can transfer attention from one symbol to another nearby symbol. And those are really vague kind of statements, but he formalized this by creating this concept that you see right here. This is considered to be a tape. This is cell number 0, cell number 1, cell number 2, and so forth. And it's infinite in the right or left to right direction, but it does have a first element. I think, if I'm not mistaken, I think that Turing's original one was infinite in both directions, with a starting cell indicated. But this arrow indicates a read-write head, if you want to think of it like that. And this is the thing that's able to read what's in this cell, and then it can take something and write something into that cell. So the next thing that you get is the ability to move on down the road. In particular, we're used to going in the forward direction, but Turing's machine allows you to go backwards as well, as long as you're not in the first cell, cell number 0. So in this case, what we've got is the ability to start here, or anywhere for that matter, and do a read of, say we read an A here and we replace it with a B. And then we move either to the left or to the right, or it turns out that we can also stay put. So still this is pretty vague, but we did end up formalizing this into a definition of what a Turing machine is, and there it is right there. A Turing machine has these parts. We have a set of states, Q. We have sigma, which is an input alphabet. We have gamma, which is the output alphabet. And we also have Q naught, which is the starting state. And we have delta, which is the transition function that tells us how to move around in states depending on the input and where we are. If you look here, that doesn't really describe this, it doesn't seem. But if you look down here, you'll see that it actually does describe that. This thing, we're going to go through this in detail in this video. A finite set of states, just like a PDF or a finite automaton, an alphabet, like a finite automaton, and then we have this gamma, which is different. It's an additional set of characters. That it's an additional alphabet, basically, and the fact is that this one has to, we're going to see, it has to be a subset of this one. Sigma has to be a subset of gamma. We have some other things that aren't described in here. For example, if you look at this, Q is a finite set of states, and there are two additional states, H sub A and H sub R, that aren't elements of Q. In other words, they have some special designation, and in fact, what it means is H sub A, if we end up in it, that says accept what we've done, and H sub R means that we need to reject it. And reject may mean reject some proposition about the words in the language, or reject the word that's on this tape altogether. Down here then, we have also another symbol, delta, which is not an element of gamma, but we can still deal with it. We have Q naught, that's an initial state, very much like we had with the Q naughts of FAs and PDFs and such, or PDAs, I mean. And then this delta looks pretty wild, but if you look at it piece by piece, you can handle it. This part says that this is the domain from which we get information. This says if we are in some state and we either read something from gamma or the actual delta, which can be on the tape, then this says that we can do this stuff right here, all of this. We can go to a triple, a state from Q, or the accept state or the reject state, one or the other, and then we can decide what we've got with gamma union delta, and we're going to look at and see what that means here in a second. And then we can say to move right, left, or stay. Now, this is going to be the character that we write to the tape in place of the one that we read. Okay, so we were in this state and we read this value from the current spot, the current position, and we go to this state, one of these states in Q or H sub A or H sub R, and we write gamma union delta, meaning either I write a gamma or a delta, and then we move the tape head right or left, or we stay put, R, L, or S. So if you read this paragraph right here, I think it'll help you understand what this delta is. But if you think about what we've got, and you take a look at this, well, let's look at this first. If we're in state P and we get this capital X, which is a character in gamma, or apparently is, I mean, it doesn't have to be there, but there could be any number of characters in there, finite number. But if that's the case, if we are in state P and we read an X, we go to state Q, we write a Y, in other words, replace the X with a Y, and do something in terms of the direction, right, move right, left, or stay. We take this whole thing and we modify it, or we describe it as a diagram like we're used to drawing finite state diagrams. And this says I'm in state P, so that's where that goes right there. And I read an X and replace it with a Y and do this direction, right, left, or stay, and I end up then in Q. We can take this kind of thing for every, or draw this kind of thing for every possible element in this domain and for every possible outcome that we can get. So there's a bunch of different ways to go about describing the same concept, but this is in fact the main concept behind the transition function. This is it in detail, but this is what it looks like. Start in state P, whatever state that is, read some character, go to state Q, write some character in place of the one we read, and move in some direction, right, left, or stay. There's other ways to do it though, other ways to describe it, and we'll use the one that is the most convenient for the thing we're trying to accomplish. This is called a configuration of a Turing machine. This means that X is a string that is things to the left of the current position. Q says that we're in state Q. Y means that the first character in Y is the character that will be read now. So this says that we're in state Q. We've got these things to the left of the current state. We've got these things, whatever's in Y, at the current state and beyond. So it seems kind of goofy because what we want to do is then to use this to describe these transitions, and we're going to get there. You're going to have to do some special reading and read this carefully and go through this and in fact read this whole thing carefully and go through this description, read this thing carefully and go through this description or consider this by reading all of this and so on. But it's not terribly difficult to read. So there's one way to describe a configuration. In other words, kind of the current configuration of the Turing machine. This is the way the Turing machine would look if you could keep looking at it. We know where the current position is. We've got some or 0 or more characters in front of the current position. We've got 0 or more characters from the current position to the end of the string, and that means the current position contains the first letter of this Y. All right, so we've been there twice now. Okay, sometimes you'll have a delta in here. Remember, delta is not a member of gamma. The blank symbol is not an element of gamma. And this generally will mean, although it doesn't necessarily mean this, at first for us it will mean that we're at the end of the input, the right end of the input. And that means that we've got all the letters on the tape are in front of the current position, which points to this delta. Now, we can write delta onto this tape, as you can see right there. That says we get to write delta on there. And presumably we could write it wherever we wanted it. We normally are going to have delta, well, we always will have delta beyond or from the end of the string, the first cell after the input or after the string on the tape, all the way out to the end of the tape, which is infinite. So every other one is there. But we sometimes will go past that and we'll store some stuff out here. And then we'll zip over here to get some information, and then we'll zip back over here to do some processing. And that'll become clearer as we go. Sometimes we write it like this as well. The sigma is sort of playing the role of the state, except we're talking about a different kind of configuration. We're talking about the fact that we've got these letters on the tape before there's a sigma, and then we've got letters on Y after that. And that sigma is the current tape cell that we're looking at. That's where the arrow would be pointing in this diagram that you see here. Okay, and sometimes we'll just flat out say XY and underline the Y, meaning that the first character in Y is the current character. This seems pretty abstract, I'm sure, and it pretty much is, but you just need to know those things to be able to read the text. You need to know what that means, what that means, what that means, what that means, and then you have to keep in mind that we use certain characters like P's, Q's, and R's and W's, things toward the end of the alphabet we'll use. This is the alphabet we use. But then here we've got a Greek letter, okay, and that's going to represent a character because it's sigma. And we might even say sigma sub 1, sigma sub 2 if we had to have several different kinds of things like that. So that means that it's a letter from the alphabet, from the input alphabet. So that's important to keep in mind, just so you'll be able to make sense of things that are coming. If Y happens to be, in this case, the lambda, the empty word, instead of writing XY underscore, we'll usually write X and a delta underscore. Even though lambda is the empty word, we'll still say that we're pointing to the delta immediately following the tape string. Okay, now keep in mind there's a bunch of things that you just kind of have to keep thinking about, and one of them is the idea that the tape content can change, and usually does. With our previous stuff, we could go left to right, finite automata and PDAs, and we go left to right. We couldn't move backwards, and we couldn't modify what's on the tape. So when we get done with a finite automaton, reading something out of a string by a finite automaton, when we get done with that, we end up with the same string that we started with. We may end up in a Turing machine with none of the same string involved. For example, and I think I mentioned this in class, I could have letters A, B, and C, lowercase a, b, and c, as part of my alphabet, but which alphabet? This alphabet, sigma, and I could have capital A, B, and C part of this gamma alphabet, which would be sigma including gamma, the capitals. So the gamma would be lowercase a, b, and c, uppercase a, b, and c. And I could read a lowercase a and write an uppercase a and move right and keep doing that until I end up reading the delta. And that means I've changed the entire word that's on the tape. And that happens all the time. That can happen. So we're going to do some configuration specifications by saying this is what the configuration of the machine is. These are these things right here. These are all the configuration ways of describing them. And we can say that if we are in state Q and it's a non-halt state, meaning it's not H sub A or H sub R, then we can write that, and this is similar to notation we've seen in the past. If we're in this configuration, we're in state Q with the first letter of Y, the current character, and X is the characters in front of the Q, in front of state, the Q in this string here. This says that we can use one move and get to this from the first configuration to the second. But we can end up with Z in state R and W. All right, so the first letter of W is what the pointer is pointing to. We're in state R, and all this stuff's to the left of the current position. Pretty similar kind of stuff to when we used the arrow. Notice here they even go one step further, just like we did before, to indicate that's an asterisk. It's pretty small to see, but that's an asterisk. And maybe I can make this a little bit bigger. Yeah, you can see that better. So this means we can start out in this configuration and eventually by using the rules of this particular Turing machine, eventually, that's the asterisk, end up in this configuration. So it's just notation that we're very familiar with anyway. If you look at this, here's an example. This says that if we're in state in state Q with AAB in front of the Q and A delta A be at the current position with this A and these two following immediately, we could write this. If delta of QA is R delta L. Read an R, or you're in state R, read a delta and move left. Okay? So if we're in state Q, which we are, and we read an A, we're going to move to state R, write a delta in place of that A, so it's going to be a delta right here that gets written, and we move left. So now the position will be on that B right there. And as you can see, that's exactly right. R is starting with B, delta, delta, which is because we read the A and wrote the delta. And we leave this A alone. So we're messing around with this string by changing pieces of it and moving anywhere we want to do the operations that we have, and we're using these configurations to describe how we can march through the tape and the states. Notice also that, as in previous situations, if we don't really need to know if it's already pretty clear what the Turing machine is that we're using, we don't put that subscript there. As you can see here, we just, instead of writing these, we're usually going to write this. Sometimes we'll be doing two Turing machines at once, and we might want to say T1 and T2 or T and S or something like that. I'm going through this like this because I want you to read these things in that grade of detail. I want you to know every blessed word that is written here and know what it means. And when they give you something like this, you need to go through it and understand precisely what that means. I've got a string of characters called X up before the current position. I'm in state Q, and the first letter over here is the next character to read, and that means I'm at the end of the word, or I'm on a delta, which is not a character in the alphabet, the input alphabet. But you need to go through it in that much detail to get a good flavor for what this book means. And this is an interesting thing. It says Turing machines as language acceptors. And what we mean by that is that what's implied, I guess, by that is that maybe there's some other kinds of things we could do with Turing machines rather than accept a language. But let's look and see what they mean by accepting a string by a Turing machine. And if you look at this, these configurations and these transitions that we're talking about really become beautiful, because now we can say this thing, if we understand this notation, and we understand this notation, and we understand that notation, we can write this relatively complex thought in just a few symbols. This is the economy of symbolism that mathematics offers us. And we can look at that and quickly understand what it means for a string to be accepted by a TM. If I'm in state Q0, and there's that delta that's the beginning one of the string, and then there's a string beyond it, and it says I can eventually get to some string of characters to the left of the current position. I'm in the accept state, the one and only accept state, and I've got strings beyond it. That means the word's accepted. And then we say that the language of T is the set of all strings over sigma star, over sigma, strings over sigma, accepted by T, where you start out at Q0, you end up in an accept state. That's a big deal. Let's take a look at this transition diagram. This is how they indicate Q naught, or they'll indicate it this way, but if not, this is how they indicate in the book for this finite automaton. Notice what's going on. I'm in Q naught. This is the FA, and this is the Turing machine equivalent. I'm in Q naught, and here I read an A and go to whatever this state is. Here I read a delta, and I write the delta back, and I move right. So this guy right here is really this state right here, because I don't have this part to do on a finite automaton. So now I'm in P is over here is this state, and I read an A and I write an A and I move right. Notice every one of these things. Whatever I read, I write back, and then I move right. And when I am in either of these two states, once I move right, I immediately read a delta, write a delta, move right into the accept state. So there's a little bit of extra stuff on the front end of a Turing machine. Everything is read a letter and write the same letter back and move right. And this thing right here is the ending is a little bit more complex, not much, but enough more complex. You got to map it. Here we just mark these guys as accept states, and instead on a Turing machine we have another state that is the accept state, and we simply read the delta that better be there at the end and write the delta. And if it's not, then the machine doesn't know what to do and it crashes. Or we could say read anything else and go to the reject state. But right there, that Turing machine is equivalent to that finite automaton. And taking that concept, I think you can look at that and you can decide that, yeah, I could do that with this transition from here to here, or this translation from here to here, from a finite automaton to a Turing machine. And every finite automaton could be written as a Turing machine. Okay? So if that's the case, that means that Turing machines accept all regular languages, because every regular language is accepted by some finite automaton, or maybe many of them, but we can take any one of those and convert it to a Turing machine, and it accepts exactly the same language as the original FA. So Turing machines have every bit of the language generating, accepting capacity that finite automata do. And as a result, they can also do all the stuff that non-deterministic finite automata can do, and they can all do all the stuff that you can generate with a regular expression, because those three, FAs, NFAs, and REs, they're all the same. They're all equivalent in their language generating capacity. And you can always convert from one to the other. And so we could, if we get a regular expression, we'll write it this way and build the Turing machine this way. So I'm going to stop right there, and that will be the end of this particular video, and then I'm going to continue on with another one.